Let me share this article from the worldwide renowned economist Guido Imbens with you. It has been published in the Journal of Economic Literature 2020. So it's about a comparison of the potential outcome approach and the PO, potential outcome approach, and the Directed Acyclic Graph approach, or DAG approach. So which one is more convenient? The well-known, well-established potential outcome approach, or the pretty new, at least for economists, pretty new Directed Acyclic Graph approach, DAG approach, to causality. To be honest, I was not aware until recently that there is such a thing like DAG. But a colleague of mine at FOM approached me and said, well, have you read this book here, The Book of Why by Pearl and Mackenzie? And I highlight the DAG approach, and it's well renowned in other fields than economics. So I waited a couple of years now to get a statement from one of the very best economists in that field, and here it is. The overall message, the take-home message is that for us, for economists, the potential outcome approach is the relatively better one. Nevertheless, we can learn something about our field if we do the DAG approach. So in the introduction, Imbens refers to the history. Causal inference goes back to the 20s and 30s, where researchers like Tinbergen, Wright, and Havelmo asked the question, why is the price high? Is the price high because demand is high, or is the price high because supply is short? So that's the identification issue. So you have two simultaneous equations, one equation for the supply curve, another equation for the demand curve, and the question that have been discussed at that time, by the way, until today, if you just look at demand curve, right, and that's what I learned from bachelor students, right, I tell them in first session, well, if the price is high, then demand is low, and that's intuitive, right? The price is high, demand is low, the price is low, demand is high. If you just look at demand curve. And on the other hand, a session later, I tell them if the price is high, then demand is high, right? That doesn't fit together because on the one hand, I talk about the demand curve, and in the second session, I talk about the interaction between the demand and the supply curve, and this is a challenge, right? And this goes back to the 20s and the 30s of the last century, simultaneous equations methods, the differentiation between if you just look at one curve or if you look at the equilibrium price. Another thing is structural and reduced form approaches. So in the reduced form, you only have the exogenous variables on the right-hand side of the equation, and the endogenous variable on the right-hand side of the equation, right? And that's the reduced form. And what is typically hard to understand if you start with economics is just to take again the demand curve, right, which is downward sloping. So if you are on the demand curve, and when does the demand curve shift? And here you are on a demand curve for a given income, and if the income variable, the exogenous variable changes, then the demand curve shifts. That's what we learn in microeconomics. So what is exogenous and what is endogenous? And this is not always easy to grasp, and that is mainly theory driven. So in this paper, as already mentioned, the potential outcome approach, which has been highlighted by Rubin, so this is associated with the Rubin causal model. Rubin is a Harvard economist. And the DAG approach, which is mainly promoted by Pearl, is discussed in comparison. And our main book here is the Angrist-Pischke, and they only exclusively refer to the potential outcome approach. Or in other words, textbook authors like Angrist and Pischke and also others, they mainly ignored the DAG approach, and as did I, but now it's the first time I come up with that in a lecture. You might ask, how could economists ignore such an important contribution to the literature for such a long time? Well, the reality is that you hardly find any papers on that, right? And the reason is that the DAG literature, so the Book of Why, so DBOW stands for the Book of Why by Pearl, mainly refers to artificial examples, to toy models, right, to make the point. And this is, for example, in contrast to other methods like RDD. RDD is also well known for decades, but has grown enormously in the last, let's say, 10 or 15 years, just because it's useful. And you find a lot of papers using RDD, and we'll talk about some in this lecture. What we also observe is that machine learning methods do play a larger role meanwhile. That's something that comes from computer science, and we'll have a session on that too. And another example is the synthetic control methods, where you synthetically construct control groups. That has also developed and has turned out to be useful. So if something is useful, then you will find papers. And DAG seems to be, sometimes a set of solution in search of problems rather than a set of clever solutions. So the smiley comes from my side. Tell me a real problem you want to solve with that model. So I will refer to the DAG model and or approach, and give you also some simulation models to check so that you can get your own critical assessment. It's not about my assessment, right? I have a smiley here, that's my assessment. You should get your own assessment, and I try to provide you the arguments pro and con. But Imbens is quite clear after having checked the approach. His assessment is, this is for toy models. It has not turned out to be very useful in economics, but that could of course change in the future. We'll see. So the main focus of the Book of Why is on identification. Identification is not that easy to grasp. So far we know that we can identify a causal effect in case of an RCT. And this is due to the fact that we get rid of the selection bias by randomization. So it's not like the positively selected group can occur, because randomization assures that there is no positive selection program group. It cannot occur that a negatively selected group comes to the program code, because randomization assures that there is no negative selection in the program group. So randomization avoids selection, positive or negative selection, or in other words, a randomization kicks out the selection bias and is a procedure to make sure that you can identify the causal effect. And that's what we know so far. But identification is more complicated, and you will see that for each method, what is the identifying assumption. And it's always about identifying a causal effect. So the directed acyclic graphs, DAG, look like that. So in case of a randomized experiment, it's just the treatment and the outcome that is clarified via a graph. And if you have unobserved variables, you could highlight the influence of unobserved variables. So these are easy ones and get more and more complicated. So an advantage might be that you get clarified what's really going on. So take a first example. So the figure 1 panel A. I'll show that in a second. So what you typically have, you have on the one hand nodes and on the other hand directed edges between nodes. And just start with a simple one, and the figure 1 panel A, there are only two nodes corresponding to two variables, x and y, and there's only a single arrow, that's the directed edge connecting these two nodes. Let's have a look on that. So this is figure 1 panel A for the randomized experiment. So you have these two nodes and a directed edge, the arrow. The direction of the arrow captures the notion that x causes y rather than some other explanations. So alternative explanations include that y causing x, as in figure 1 panel B. Check that. So this is B in figure 1, and this arrow here, this directed edge, stands for that the causality could go either this way or the other way around. That's what we call reverse causality. You might have a look to figure 1 panel C, and here unobserved factors, unobserved variables, U denoted by a circle rather than a solid dot to denote that it is not observed, causing both, as in the spurious correlation figure 1 panel C. So that's panel C, the spurious correlation, the unobserved, and causing or influencing x and y. So I don't want to go through the whole article, but a second figure might be useful with respect to our lecture, and that's figure 2. Here you have a so-called confounder, a so-called confounder, and the confounder is W, and the confounder has an influence on x and y. And that's something we need to know. So the effect is confounded by the effect of W on x and y. And how does the figure look like? So it looks like that here. So the W is the confounder, and the X and Y is confounded by both. So that's a scenario we will need when we talk about the matching approach. Especially we'll go through propensity score matching. And why is that relevant there? Well, on the one hand, you have in the matching approach now, the treatment, and on the other hand, you have the outcome, right? And you need confounders that influence both the treatment and the outcome. And these confounders are variables that can be observed. So this means can be observed, can be observed, can be observed. Variables that can be observed and influence both the treatment and the outcome. And all these confounders should then be included into the propensity score. So you don't understand that now, but after the matching session, I will refer once again to that. So this is something that is quite useful, and without having used the DAG approach so far, I've done that in my previous lectures with exactly this graph. So the graphical exposition makes also clear how an instrumental variable IV estimator works. So I think that's quite useful because then you can show on the one hand what is your outcome variable, and on the other hand what is your explanatory variable, and discuss, well, this explanatory variable is, and we'll see that when we go through IV, is endogenous. And because it is endogenous, because we need an instrument to instrument the endogenous explanatory variable. To do that, we need a positive or negative covariance between these two guys. That's then the first stage. That should be meaningful, right? But it's endogenous because there are some unobserved factors. So this stands for unobserved factors that influence X, Y, and X. So you could clarify what you're really doing. And that's the reason why I think such a graphical exposition might lead to more clarity what you're really doing. So I will use that as in previous semesters in my lecture. So by the way, Imbens also agrees with the book of Y that the DAGs are superior in clarity. So it's about getting clear what's going on here, right? And it's a non-technical approach to that issue rather than just to look at expected values and covariances. Now let's repeat the potential outcome or the Rubin causal models. I have done that in previous sessions, however, maybe not that clear with respect to the terminology potential outcome, right? So the tau is the average treatment effect. The average treatment effect in expected values is the mean outcome of the program group minus the mean outcome of the counterfactual behavior of the program group had the program group not participated in the program. So you know that story. So in other words, there are, in a binary treatment case, which is the easiest one, there are two potential outcomes. One is y0, or y0 could also denote it like that, and the other one is y1, or you denote it like that, y1. And if you observe the outcome in case of non-participation, then the counterfactual is the other potential outcome in case of participation, or you observe the outcome in case of participation, then your counterfactual, your potential outcome, is the hypothetical outcome in case of non-participation. So only one of these potential outcomes can be observed, namely the one corresponding to the treatment received. The others are ex post counterfactuals. And the causal effect corresponds to the comparison of the potential outcomes, of which at most one can be observed with all the others missing. And that's what is called the fundamental evaluation problem. Potential outcome and econometrics, just as a repetition, right? So we have two potential outcomes, y0, y1, and the causal effect is a comparison of the two, say the difference between these two. This is simple but powerful as a notion. Last century economists like Tinbergen, they carefully distinguished in their notation between the price as an argument in the supply function and in the demand function, and the price as an equilibrium price as a result of the intersection of demand and supply functions. Here, the RCT is once again highlighted in having the Deaton-Cartwright critique in mind, right? So nevertheless, RCTs are the relatively best, and more than 100,000 experiments were conducted in 2018 by the tech companies, right? So more than 100,000. Just to make clear that the RCTs have become very, very popular since big data are available. To sum up, I will use that approach several times during the lecture. It deserves the attention of all researchers, and that's also why I use that here. It does not only deserve the attention of all researchers, but also students' attention. So let's use that for the sake of more clarity.